Newton's method for calculating pi. Here's Newton, and here is the diagram that he used. This is a description of the method Isaac Newton developed for calculating the area of a sector of a circle. This method was the subject of a famous Veritasium video, but you would not be able to figure out the exact method from that video. This calculation was covered by many others, including Matt Parker. This video was created to help you see exactly how to repeat the calculation as Newton did it 360 years ago. It will also show you how to generalize the calculation to see how you could calculate the area for different sector angles. So let's get into it. Newton's idea was to start with a semicircle of radius 1/2 and to center it at 1/2, 0. So from this diagram we can see that there are zeros at 0 and 1. It's in fact a square root of a polynomial of degree 2, and it can be factored. So let's see how to derive the polynomial. So we'll start with a circle of radius 1/2 and centered at 1/2, 0. And then we're going to solve for y, and it will factor nicely into square root of x times the square root of 1 minus x. In another video a few weeks ago, I showed how Newton solved for the expansion of the square root of a polynomial. Newton found the first few terms of the sequence b sub k such that the square root of 1 minus x is equal to the summation of b sub k times x sub k. You could think of the right-hand side as a Taylor series expansion. He observes that there was a pattern in the sequence of b sub k. The previous value of b sub k could be multiplied by this ratio, 2k minus 3 over 2k. Therefore, x was this expression, and we could find the area under the curve. This is the blue area here. We could find the area under the curve using integration. So we'll integrate this expression x times the square root of x times the square root of 1 minus x. And we'll put in that series substitution, and we'll get these expressions. And the coefficient is 2 over 2k plus 3. Now the remaining area of the sector is a triangle, the orange triangle, and that's straightforward to calculate. It's 1/2 r squared times sine theta times cosine theta. In this case it's 1/16 sine 2 theta. So we can also solve for x star. It's equal to 1/2 1 minus cosine theta, which is equal to sine squared theta over 2 times 1 plus cosine theta. So exercise 1, we're going to let theta equal pi over 3, and x star in that case would be 1/4. Newton chose these values because they made the calculations simpler. Use a spreadsheet to find the area of the two pieces of the sector. Hint, use the fact that b sub 0 is equal to 1, b sub k is this ratio times the previous value. And this is the key. The b times x to the m term is the lagged value of the same term times x times this ratio. So how many steps are required to get an estimate that is accurate to 15 digits? That's the limit that Excel can give. Let's go to the spreadsheet. All right. So we can put in the values here. 3 is the number of sectors. X is 1/4. N is the number of the scaling factor, which is 8 times the number of sectors. And the triangle here is the scale factor times the 1/16 times sine of 2 theta. In this case, it's the square root of 0.75. Now, this integration constant is 2 over 2k plus 3. The ratio is, numerator is 2k minus 3 divided by denominator, which is 2k. X is just that 0.25 number from the top. Didn't need to create a whole column for that, but there it is. Okay, the first term is the scale factor times 1 times x to the 3/2. The next term is the previous term times the ratio times x. Now we multiply by the constant of integration. That's the 2 over 2k plus 3 term. The area under the curve is the sum of these terms. And the full circle is the area under the curve plus the triangle term. And it should equal very close to pi. The rate of convergence is the ratio of the terms. It starts off small, but it increases to something close to 0.25. Okay, the number of terms, it's 19 plus 1. 20 terms are required to get 15 digits. We can generalize the calculation of exercise 1 to solve for any value of theta. One interesting case is theta equal to pi over 2, which is actually bigger angle and a bigger value of x. But the interesting thing is that we wouldn't get a triangle. So when we calculate, we get this expression for pi. Pi is equal to 8 times the square root of 2 times this expression, which is 1/3 minus 1 over 20 minus some other terms. It keeps going, but they're all simple ratios of integers. This formula for pi is not very practical, but it's kind of interesting. And let's do this calculation. Let's calculate an estimate for pi when theta is equal to pi over 2. How many steps are required to get 15 digits, which is the limit that Excel will give you. So all we'll have to do is go back to our previous calculation and change the parameters here. Here we use the x is equal to 0.5. There's no triangle. And And then we'll have to add some terms because it didn't converge after 26 terms. It looks like it's 37 terms are required for it to converge. 36 plus 1, 37. Which is more than the 20 that were required when we used pi over 3. So we can solve for different values of theta. The advantage of choosing a smaller value of theta, we get fewer steps. But the disadvantage is that the calculations become harder, especially if you're doing it by hand. Excel is not going to care. But if you're doing it by hand, X star is rational. That means a bigger calculation. And remember, we have to calculate both X star and the square root of X star. So it takes a little bit more work. But let's do that. Let's estimate the value of pi for these values, pi over 6, pi over 12, all the way up to pi over 96. How many steps are required to get an estimate that is accurate to 15 digits? Let's go back to the spreadsheet. So, well, the first value for 2, we already calculated that. The other ones, we'll do it the way we have before using the half-angle formula. So for theta equal to 90, we're going to say, well, cosine is 0 and sine is 1. For theta equal to 60, we're going to say that cosine is 0.5 and sine is the square root of 0.75. Those are values we know. And then for all subsequent ones, we'll use the half-angle formula. So this is the square root of 0.5 times 1 plus cosine theta. Okay, that should be 0.5. Yeah, 0.5 plus 1 plus cosine theta, or the previous value. And then the sine value is the previous value of sine times 2 times the cosine value. Okay? The triangle, this is the 1/16 sine 2 theta. So we'll use that formula. Here we can use the actual value of sine 2 theta. The n is the scale factor, and that's always 8 times the number of sectors. The scaled up triangle is just the scale factor times the triangle. And x, remember that's 1/2 times sine squared over 1 plus cosine theta. We'll bring those values down. Now we'll highlight the table area. And we'll hit the formula, and we'll hit the define names, and that will create a pop-up window. It looks like this. And we'll type in table 2, and that defines a name for that region and allow us to pull in values from another spreadsheet into this spreadsheet. So we'll use a lookup table, VLOOKUP. We'll use the value in D2, cell number D2, in table 2. And we have to remember the column. For X, it was 7, column number 7. For the scale factor, it was column number 8. For the triangle, it was column number 6. Okay, that's the data. And if we change the number of sectors, we can populate that with the different data. And we get the calculation. Now we're going to put in 6 and see how many steps it would take. And we see that it would converge after 10 steps, which is half as many as it did with n equal to 3. With 12, the triangle turns out to be 3. That's nice. And the number of calculations required is only 7. When n is 24, that drops down to 5. We're kind of getting diminishing returns on this. So 48, we get to 4. And 96 will get down to 3. Which is good, but keep in mind, if we were going to calculate this to 50 digits, this is the way to go because it would converge after only 14 steps. Newton myths. This method is associated with several myths. Myth 1. This method uses integral calculus invented by Isaac Newton. This method does use the area under the curve. However, mathematicians of Newton's time were able to find the area under several types of curves using non-calculus methods. Much of Newton's work here was based on techniques developed by English mathematician John Wallis. Myth 2. Newton's method was a huge improvement over previous methods for calculating pi. This method has the same rate of convergence as the previous pizza slice method, which we discussed in a previous video. It takes the same number of terms. It does require fewer irrational number calculations, so if you're doing it by hand, it could be faster, but only if you didn't have to calculate those b terms. Okay, Newton's method led to better methods for calculating pi. No, actually the big improvement for calculating pi was our arctangent formula. That was discovered by Gottfried Leibniz and other people, Madhava and Gregory. Madhava discovered the arctangent formula nearly 300 years before Leibniz did. All right, time to close the spreadsheet. Thank you.